In this lecture, we give a new definition of norm and trace, and this is linked to the previous definition via the characteristic polynomial and therefore the minimal polynomial. So let us state the proposition first. So let L over K alpha this be extension of degree m, and the minimal polynomial of alpha, so this alpha has roots in some splitting field, say alpha 1, alpha 2 all the way to alpha n. So we are considering this extension here, L over K alpha, but when we talk about trace and norm, we are going to talk about L over K. So you have to understand that this m actually comes from the degree of extension here, but we are talking about trace and norm in this extension. So trace of L over K of alpha is m times the sum of these roots. So you add all the roots and multiply it by this m here. So again, this L over K alpha is m, and here it is L over K. Similarly, norm L over K, you multiply all the roots and raise it to the power of m, where this m is this degree of extension L over K alpha. So this is what we have to prove. So let us start with the proof now. So let f of x be the minimal polynomial of alpha of degree d. So since some splitting field you have these roots, so you can write f of x as product of x minus alpha i's, where I goes from 1 to d. You can expand this out, you will get a polynomial in degree d. And from here, this expansion here, you can see that the sum of the roots, all these alpha i's, is precisely encoded here. So c1 is minus sigma I alpha I, and this constant term is just the product of the roots cn, and you have to take into account this minus 1 here, and this minus 1 is raised to the power of d because d is the degree, so you're multiplying d times, and then you have the product of alpha is here. So this just comes from the expansion right here. So you expand it and you will get this c1 would be this, and cn here constant term would be this. Now in the previous lecture we showed that this characteristic polynomial of x of alpha over field extension L over K was this minimal polynomial raised to the mth power, where m is this. So therefore now you raise this entire thing to mth power, so this entire thing to the mth power, so you have to raise this thing to the mth power, this thing to the mth power, so you will get some polynomial like this. So again, once you have the characteristic polynomial, then you know exactly that this term with the negative sign would be trace, because you have positive here. So you have trace here and you have norm right here. So this is the property of the characteristic polynomial. Once you expand it, you will get the trace here and norm here. So the trace is this coefficient minus mc1, but you know c1 is right here, so you copy this here, so you get m summation of alpha I. So we have proven this statement, and norm is this minus 1 to the power of md cnm, and this is precisely here, right here, and then you copy it right here, raise it to the power of m, and so you will get md plus md 2md. So because you will have 2md here, so minus 1 to the power of 2 will kill this minus 1, so only thing you're left with is this, and that's what we wanted to show here. So now we want to give another definition of norm and trace, which would use Galois groups. So essentially just a reformulation of the statement here, or this proposition. So let G be the Galois group of this extension L over K, and say this is a finite Galois extension and alpha is an element of L. So then we can say the characteristic polynomial corresponding to alpha L over K of x is just product of over this sigma belonging to the Galois group and x minus sigma of alpha, so wherever this alpha gets permuted by sigma. So this is what we want to show. Now if you start expanding it out, then you know that the term corresponding to say xn minus 1, the second term here, just like here, will give you trace. So your trace would be just the sigma alpha, just like here. So if you expand this out, the coefficient of which is just 1 degree less than the total coefficient will give you the trace, and the norm is just the product of the constant terms here. So just by expansion of the characteristic polynomial, we have seen multiple times before how to obtain the trace and the norm. So this will just come about from the expansion of this. So just like here, so every time you expand the characteristic polynomial, this term gives you the trace, which will be the sum of the sigma alphas, and constant term give you the norm, which will just be the product of sigma alphas. So this thing will just follow from here. So we have to prove this. So essentially we just have to prove this statement. Now to prove this statement, what we will do is we will construct a minimal polynomial and show that this is equal to, so minimal polynomial obviously of alpha. So say f is minimal polynomial of alpha. So we will show that this is equal to fx to the m, where m is just as our standard L over k alpha. Notice that extension we are talking about is L over k, but this m comes from L over k alpha. So we show this, and this we have shown before. So before we have shown that this is equal to the characteristic polynomial of alpha L over k. So this we have shown before when we linked minimal polynomial with characteristic polynomial. So this is what we need to show. So again, expanding the characteristic polynomial will give us norm and trace. So you start with f of x as a minimal polynomial of alpha of degree d. So now we do the same thing what we did here. So now you have product I equals to 1 to d x minus sigma I alpha. Sigma I alpha are all distinct. They are distinct precisely because we have a Galois extension here. So L over k is separable. Separable means that the roots are going to be distinct. So this is it. So now we want to raise it to the power of m, where m is something like this. So for this we have to link two things. We have to link these sigma i's with this sigma right here. So only then we can move forward. So let H be the Galois group of L over k alpha. So precisely because we want to talk about this, so you know the order of H is now m, because m is this degree of extension here. Just copying this right here. So H is this Galois group. So what does this H consist of? It consists of homomorphisms tau, which will fix k, but will also fix alpha. So tau of alpha would be some alpha if tau lies in H. So this tau is an element of H. So how are these two related? Sigma alpha and sigma I alpha. So these two are equal if and only if, so this sigma I tau of alpha is equal to sigma I of alpha alpha, because tau is fixing this alpha, and we have to use this m somehow. So we have to talk about this Galois group. We don't have an option. We want to raise it to the power of m here. We don't have an option. So sigma alpha is equal to sigma I of alpha, and this is possible if only if sigma lies in the left coset of H. So H consists of these taus, and you can see this alpha to be fixed here, we have to compose it with some tau alpha, which is anyway going to fix alpha because this tau lies in H. So these sigmas actually lie in the left coset of H. Now sigma is running over our Galois group G, and we are asking the question that sigma alpha is running now over Galois group G. You are applying it to alpha. How many times we will see sigma I alpha appearing? So sigma alpha is some number, sigma I alpha is some number, or some element here, some element here. How many times we will see sigma I alpha repeating itself if we are going to run this sigma alpha over this Galois group G? So the answer is sigma lies in the left coset of sigma I of H, and therefore as this sigma will run over the Galois group, this sigma I alpha will keep appearing this as the order of H times, because this lies in the left coset. So sigma I alpha will occur order of H, which is m times, because this is m right here and the Galois group is L over k alpha. So we are we obviously want to link this sigma alpha to this sigma I of alpha. Only then we can prove the statement. So now this thing would be equal to, you have the product x minus sigma I alpha occurring m times, because this has to happen for every root of f. For every root of f we have to have this. So so therefore you will have this m here, and this is precisely fx to the power of m, and which is equal to our characteristic polynomial which we wanted to show. So now an example. So consider this field extension. You have joined root 2 to rationals over rationals, and the elements are of the form a plus b root 2, where a and b are rational numbers. So say sigma 1 is just the identity map, and sigma 2 puts a negative sign here. So then trace of this extension is just the sum. We are using this, which will give you 2a, and norm is the product, which will give you a square minus 2b square, and the characteristic polynomial is just this, which will give you x square minus 2ax minus a square minus 2b square. So we can replace 2 with any d, which is a non-square rational number. So instead of 2 you put in d, instead of root 2 you put in root d, and you can repeat this argument. Now there is a big theorem whose proof is long and tedious. So say you are given extensions like this. You have L over K and then M over L. So trace of M over L, so this is M over L and this is L over K. So you take trace for the first part, compose it with trace of the second part, you get trace of M over K. Similarly for norm of M over L composed with norm of L over K is norm of M over K, as you would expect. Now this is a big theorem and takes couple of pages to prove, and the best source to see it is this book, Basic Algebra 1, on page 426, and this book is by Jacobson.